record. All right. So t-tests. Everybody's been waiting for this, right? Everybody's been super. When are we going to get to Be the fool doesn't know his population standard deviation. Important thing, Mr. T-test. All right. So thing is up to this point, what we've been doing is we've focused on our hypotheses testing, where we've got a sample mean, comparing that to a population mean with a known mean invariance. Okay. This is our single sample Z test, right? And this is fine. Again, in our basic demo here, we're working from, we've worked a sample of treated rats, right? And we know that the normative population of rats have a mean weight of 400 grams and a variance of 50 grams, right? And so what we can do is measure the characteristics of our sample rats, compare them against a known mean and variance or a known population mean standard deviation, and say, if these sample rats do come from a population. Now the population is hypothetical, right? This might be 20 rats, these are the only 20 rats in existence who have received this treatment, right? But we're assuming that there's some population, hypothetical population of treated rats. If we were to treat all the rats with this, would produce a distribution having some value, population value for weight and for mean and variance in terms of weight. And we're saying, are the characteristics of this sample of treated rats, are they likely to have, what's the probability that they've come from some population with mean 400 variance equal to 50, okay? And this is our standard sort of setup for our one sample Z test, okay? Problem is that single sample Z almost always requires more information than we have at our disposal, okay? What we need in order to calculate that Z test is we need to know our population variance, right? So we need that population variance to calculate our standard error of the mean, right? But in general, we don't know what that population variance is. And if we don't know the population variance, we're missing an essential piece of our test. So what do? Okay. And so solution we could do, right, is we know that our sample variance, if we calculate it correctly, as we've sort of walked through, we know that our sample variance is an unbiased estimator of the population variance, okay? And so what we can do then is use the sample variance to estimate the population, or to estimate our standard error of the mean for our hypothesis test, okay? So pretty straightforward. Okay, I don't know what the population standard deviation is, but I've got this sample. This is the variance or the standard deviation of the sample. I know that if calculated correctly, is an unbiased estimate of population value. And so therefore, I'm just going to plug my sample variance in for my population variance in my test statistic. And I'm just going to go ahead and use this. Okay. And so again, remember that our formula for our sample variance is going to be a sum of our squared deviations, right? And we take that sum of squares and we divide it by n minus 1. Katie, why do we divide it by n minus 1?
Because that's the population.
That's the sample, the sample formula. Yeah, here. Do you remember why we divided by n minus 1 instead of n? What is that n minus 1? Does anybody help her out? It has to do with degrees of freedom. Emily?
Doesn't it help minimize error?
Yeah, it sort of starts to bring it in, right? Because if we go through and if this is the population variability, right? This is the variability of my population. If I just go through and pull a true random sample, where's my sample going to come from? It's going to come from the middle, right? And so what happens is if I just calculate my sample variance using the population formula, my sample variance is always going to be smaller than the population. It's going to underrepresent it, right? Because most of my stuff is going to come out here, right? So what we do is we go through just a very small correction, right? We divide our sum of squares by n minus 1. And Sam, what does that, if I divide by n minus 1 instead of n, what does that do to my sample estimate? It increases, it makes it better, it corrects for that underestimation using the population. And so same if I have a very small sample size, what's that correction going to be? Is it going to be big or small? It's going to be big. And if I have a really large sample, what's that correction going to be? Pretty small. So as my sample gets bigger and bigger and bigger, I'm going to expect it to start catching those things out at the end more. But if I've got a small sample, probably they're just going to come out from the center of this, right? So what we do is we go through and we, if we use the proper sample formula for the calculation of our variance, of our sample variance, then our sample variance is an unbiased estimator of that population parameter. And we're pretty happy about that, right? So in terms of getting this formula in, using this to calculate my sample variance is an estimate of my population variance. We know that my sample variance is unbiased, but problems arise when I start looking at the sampling distribution of my variance estimates. Okay. Someone tell me what a sampling distribution is. Okay, so that's a distribution of sample means is an example. So Matt, expand on that. Sort of what is a distribution of sample means?
All of these sample means added together into a distribution.
Yeah, so it's all the sample means that could be pulled from a sample of a certain size from a population, and if we plotted all those means out, we get a distribution of means. Okay, same thing with variances. Sampling distribution of the variance is if we were to say pull all samples of size 100 from a population and calculate the variance of all those samples. If we were to plot those out, that would give us a sampling distribution of the variance. Okay. Problem is even though our sample variance is an unbiased estimator of the population variance, funky things start to happen when we look at that sampling distribution of the variance. My sampling distribution of the variance, again, the distribution of all variance estimates that could be obtained from all possible random samples of particular size could be drawn from the population. But Elizabeth, when we talk about the distribution of sample means, what's the shape of the distribution of sample means? What do we know what is our distribution of sample means? What shape does that approach very quickly? Yep. Yep. So we know that our distribution of sample means starts to approach normality under two conditions. What are those two conditions? Yep, if I've got reasonably large samples, even if the thing that I'm studying has a big skew or is kind of funky, as long as I have reasonably large samples, that distribution of sample means starts to approach normality very quickly. What's the other thing?
The underlying construct has a normal distribution.
Yep, if the underlying thing I'm measuring has a normal distribution. So under those two conditions, what we know is the distribution of sample means starts very quickly to assume a normal distribution. Sampling distribution of my variance though, different situation. Sampling distribution of my variance evidences a positive skew, particularly if I'm working with very small or smaller samples. What I get is a sampling distribution that's not normal. It's characteristically skewed. Okay, and if we think about why this is, Teresa, can I have values of the population that fall below the mean, or sample means that fall below the population mean? Yep. And can I have values that fall above the mean? Yep. And under a normal circumstance, we would expect things to kind of curve out, right? What about variances? Can I get like negative variances? What do you think? Yeah. Yeah, because essentially we're saying my variance is less than 0, which doesn't make it can't, right? And so what we end up is, as opposed to our means, right? Our variances are kind of bounded by 0. They kind of get stacked up here. Now, can I get variances that are very, very large that overestimate the population value? Yeah, I can do that, right? So what we end up with, particularly with small samples, is a distribution of sampling variances that doesn't follow normal. Distribution of sample means nice normal curve, easy peasy, no worries there. Distribution of sample variances, though, that sampling distribution is skewed, right? And this gets worse with small samples. And so what we see is the expected value of the sampling distribution is equal to the population variance. Okay, if we take a look right here, this value, the mean of this distribution, is equal to the population variance. So it's our, the expected value of the sample variance based on this distribution is unbiased. It's an accurate metric of our sampling of the population variance. Okay, so we're not worried about that. But Josiah, if I were to go through and look at this distribution, okay, so here's my mean, and the mean of that distribution is equal to my population variance. But if I were to randomly draw any single study or any single sample out of this distribution, where is it likely going to fall? Yeah, it's going to fall there. The tail of that distribution drags it out, right? And so the tail of that distribution makes sure that the mean of that distribution is equal to population variance. But for any individual trial, I'm much more likely to pull something that's down here than down here. The weight of that distribution is skewed, it's too far to the left, right? So for this, Sam, if this is the mean, where's the median at? Okay, so here's the mean, right? The mean takes in everything, starts dragging it out. Where's the median or the center value, middle value? You don't have to give me an exact number, but where's it going to fall relative to the mean? The left, right? Your middle value is going to be here somewhere. The density of this is pulling it. Where's the mode going to be? To the left of that, right? So if I'm pulling any individual sample out of this distribution, even though the mean of all possible sample values is equal to the population variance, any one given my individual test, my individual study that I'm running is going to be lower more often than not than other things. Okay, and so what ends up happening is we're using sort of population norms. So if we try and use that Z curve where we're assuming everything is equal there, what we're doing is now we're working with a different distribution that doesn't follow that normal curve that starts to cause us problems in terms of our inference. Yeah.
So are these sampling distributions and variance, are they always skewed, or are they just like skewed when like it's a small n?
Yeah, it's gonna, as that sample starts to get bigger and bigger, it starts to become less and less. But this is where we start to go into some of the small sample work with the development of our T distributions. Okay, and so this is why, again, if you start working with bigger modeling programs like sort of M+ and things like that, if you're running SEMs, they don't worry about t-set tests. It's all sort of Z ratios, because the assumption is if you're using this estimator, you've got big enough samples so that we don't have to worry about this anymore, right? But historically, for the types of studies that we've done in psychology and other fields, this is a big issue, and it starts to produce biases in our inferences. Okay, so what we've got, person credited for cracking this nut, gentleman named William Seeley Gossett, published under the name Student. Okay, Gossett was a chemist for Guinness Brewing Company, and working with the limitation of small sample statistics, right? Because at this time, pre-Gossett, we're just using Z statistics to go through and do things, but like things aren't turning out the way they should under this because I'm working with unknown population parameters. And so what Gossett did was derived the formulation of this T distribution, okay? And our student's T, our T distribution, what this is doing is it's specifying the sampling distribution of the test statistic T, which uses our sample variance as an estimate of the population variance, okay? So if you think about that normal curve, think about the normal curve as your sampling distribution of Z statistics, right? This is what that Z statistic should do, assuming that the null hypothesis is true. What Gossett did was develop a family of alternative distributions known as the T distributions that follow the function as soon as we start substituting the sample variance for the population variance, okay? And so what we see is our T distribution. So if I give you your Z table, right? That's just one set of values, right? It doesn't matter sort of what we're doing or how many people in the sample. If we're working with population estimates, The Z distribution is the Z distribution. T distribution, this is a family of curves, right? And a family of curves that have a slightly different shape based on the number of degrees of freedom in our test, okay? Now, as this T distribution, as our degrees of freedom start to approach affinity, that those T distributions approach the normal curve and actually do it reasonably fast. We don't have to get to infinity before that starts to take place. I went through question just in general, sidetrack, plotted this out just so, or printed this out for you all just so you can go through and see things. I usually sort of come in here with pages and pages of handouts to pass to you all so that you can go through and use them. I'm getting the increasing idea that people are not interested in my paper handouts for different types of things. They're all posted on WIO courses. If anybody would like, if they're old cantankerous professors are wanting to be one and like to write things out on pieces of paper, I see some people are sort of, let me know and I will print those out for you to have to sort of write notes down, sort of SPSS output, things along those lines. If you're just going to sort of use your tablet electronic, just let me know, and that way I won't waste a bunch of resources for things that you don't want anyway. Okay, so just let me know. But did print out the table because that's just one page and that's easy peasy. So what would you do if you go through and take a look at this? You'll see that Emily, what is for p equal 0.05? What are my criterion values for my Z statistic at alpha 0.05, plus or minus what? 1.96, right? And so you start to see, even with 100 degrees of freedom on the level of significance for two-tailed tests, if you find the 0.05 on this and run down to 100 degrees of freedom, right? This would mean a sample of 101 if you were on a one-tail or a one sample t-test, 50 and 51 if you're running two sample t-tests. You see that cutoff value starts to get very close to 1.96, right? But Emily, as we work up the scale and we get fewer and fewer and fewer degrees of freedom, what happens to the critical value for the p equal 0.05 for a two-tailed test?
Bigger.
It gets bigger, right? And if this is my critical value, if this is the criterion that my test statistic has to pass in order for me to claim an effect, what is that doing to my test? Is that making more? Is it making it more liberal and more stringent? More stringent, right? I have to find a bigger test value to go through and claim statistical significance than if I were working with a Z value, right? And if we think about this, this makes some sense. So, Josiah, with my sampling distribution of my, looking at the sampling distribution of my sample variance, or the sampling distribution of my sample variance, for any individual value, is it likely to be high or low? For my sample variance, is it likely to be below the mean or above the mean? Below the mean, right? Which means I'm going to underestimate the population variance. What do I use the population variance to do? Where does that go in my test statistic? Goes into the calculation of my standard error, right? And my standard error is my variance estimate divided by the square root of my sample size. So if I've underestimated the population variance, Teresa, what does that do to my standard error? It gets smaller. Then my standard error goes in the denominator of my test statistic. What does that do to my test statistic?
That will, like if your denominator is smaller, that will.
Yeah, right. And so what happens to my test statistic if I'm just plugging in the sample variance, calculating my standard error, and just using my regular Z table to do things? My test statistic is too big. So am I rejecting the null more often or less often than I should? More often, right? So I'm sort of making way too many type 1 errors, right? I'm saying that, hey, there's an effect here when there in fact isn't. What I've done is I've underestimated with my individual sample, on average, underestimating population variance, which makes my standard error too small. My standard error too small. My test statistic is too big, and if I'm just plugging that into it, pretending it's a Z when it's not, when that test statistic doesn't actually follow Z distribution, what I end up doing is I end up saying that things are significant when they're not, and then my beer's all skunky and bad, right? So what Gossip was went through and said, okay, what happens? What is the distribution that this test statistic follows if I'm substituting my sample variance in for the population variance? And what we did is we then end up with a sampling distribution of T. So that our test statistic, we're still calculating this the same way as we did Z. There's nothing crazy or different, or we're still taking our sample mean divided by a population mean, right? We're assuming we still have some reference value there. And then we're dividing it by the standard error, okay? Standard error is now just my sample standard deviation divided by the square root of n. Or if you'll see, standard error same thing, same difference, right? So so this is how I'm calculating my standard error. But what we see is the shape of this sampling distribution. So I take these T statistics, assuming the null hypothesis is true, and start plotting these out for all samples that I could obtain of a given size. What I see is that as my degrees of freedom change, and degrees of freedom are linked to your sample size, as my sample size gets smaller and smaller and smaller, it starts to make that distribution become more peaked and kind of flatter tails. As my degrees of freedom get bigger and bigger and bigger, I get closer and closer to the Z distribution where things start to approach normality. Okay. And again, if we look at that Z table or that T table, as my degrees of freedom get smaller and smaller and smaller, means my sample is getting smaller and smaller and smaller. My critical values to claim statistical significance for my test start to get pushed farther out there, right? What this is doing is essentially correcting for the underestimation of my population variance by using my sample variance here. Are people at least sort of getting a vague sense of kind of what's happening with this? So, someone, I'll pick on Basha. Can you tell me what is this? How do I interpret this? What is this thing here? Yeah, this figure. What does this represent? How do I interpret this standard error from a practical standpoint? What is this standard error?
I don't remember what that's.
Okay, well, this is my standard deviation divided by the square root of my sample size, but conceptually, what is the standard error? How do we understand this?
Standard deviation of the sample distribution of means.
Okay, yeah, that's, thank you. Matt, to jump in, this is just a standard deviation estimate, right? But it's the standard deviation of my sampling distribution, right? It's telling me from statistic to statistic, how much should I see sort of relative to one or the other? How much should this jump around? How stable should it be? How close to the actual population value it is, right? So again, standard error is standard error is standard error. Standard error is always just going to be the standard deviation of the sampling distribution. That's all it is, right? It's just a variance measurement. So, but it starts to tell us, we can start to interpret this as some level of precision, how much we're expecting something to jump around, or how far any two values are likely to be from one another on average, or how any individual observation is likely to fall from the true population value. All right. So one thing to note here is our T distribution, classic example of a leptokurtic distribution. Okay. Leptokurtic, is that positive kurtosis or negative kurtosis? People having a hard time remembering? No worries, student has your back with a slick illustration from 27. Like, this is a pretty cool thing, I guess you could do back in the day. You just do some drawings, like throw in, like, in any case, readers may be unfamiliar with the term kurtosis, mesokurtic. There's some different stuff going on there, but it's basically, I bear in mind the meaning of the words, where the first represents platypus, the second kangaroos, but for lepping. He's like, but they could have been hares. Like, well, draw hares, man, instead of kangaroos. Like, I don't, I'm not sure. You critiquing your own drawing there. I might spike that view. Like, I don't know, you should use hares. But anyway, Would strongly recommend for all of your thesis to include some sort of illustration that you've created on your own. Hand-drawn stuff, that's immediate pass. Okay.
Is that like his actual drawing?
Yeah, that's literally from his article in 27. And the reviewer's like, that's pretty slick. All right, we'll publish that in wherever they publish it. But all right, here's our T distribution going through. We will probably not use this a whole lot. Today, we don't have to use tables because we've got the power of the interwebs, and we can go through and we can use p-value calculators to go through and just calculate p-values directly, as opposed to calculating critical values and then sort of saying this is going beyond the critical value. I'm just going to still have you do that a little bit, just so you get some practice in trying to solidify that process. We can do that from our t-distribution table here. We'll see almost always we'll be working from this two-tailed test. Here we've got degrees of freedom in the column. Here we've got our level of significance, and then can go through and find our critical values based on this. Okay. Also, sometimes you'll see, if you notice that on that table, we start with individual degrees of freedom and then start making jumps in terms of where things are at, right? Back in the day, we would just kind of default to the lower value because that's probably going to be more conservative. Today, we don't need to do that. We have critical T value calculators and stuff like that that you can just say, what's the critical T for degrees of freedom 47, and it'll just tell you it's a more accurate way to do that. But just wanting to know your way around this T table here. So we're kind of putting it all together here. What we've got is we've got a Z test. And what our Z test is going to do is it's going to tell us whether a random sample mean is likely to have occurred in a population given an assumed known mean and standard mean and variance. Okay. And if I reject the null, I interpret that as evidence that the data are unlikely to have been drawn from a population with this given mean. Okay. But what I need to do if I don't know the population variance, which we rarely, if ever, do, what we're now using is our T distributions, right? And our single sample T test is going to be used when we're comparing our sample mean to some known reference population value when the sample variance or the population variance is unknown. Okay, our T distribution corresponding degrees of freedom. These are going to correct for the systematic underestimation of the population variance under the sampling distribution of our sample variance here. Okay. Again, this is kind of a tricky thing to wrap your head around. Sampling variance is an unbiased estimate in that the mean is equal to the population mean, but any individual sample, because that's skewed, is going to fall too low, which means we'll go through and for any individual sample underestimate. So we need to use our T distribution, which is now a family of statistical distributions for T that change depending on our degrees of freedom, right? Threshold for our interpretation starts to become greater for smaller versus larger sample sizes, right? As our benchmarks, our goalposts start to get farther out, and the requirement for our test statistic has to get larger and larger and larger for us to sort of claim that interpretable effect as our samples get smaller. And then we can find our critical values indexed in that T table there, okay? So this is a lot of stuff to throw at you. A lot of it's kind of theoretical types of things. I want you to have that so you understand like what this is, what it means, what we're doing, and why we use it. When we're actually taking an applied approach, we're just doing, it's the same procedure we use for Z, we're just using a different table essentially. And now instead of having one set, like so one critical value for all Z's, if it's 0.05, now we're going to have different critical values depending on the number of degrees of freedom in my test. All right, so factors in influencing my test statistic. It's going to be the difference between my mean and my population and my reference value, my population mean. Sam, as the difference between my observed mean and my reference mean starts to increase, what does that do to my test? Yeah. Yeah. right? As the observed difference gets bigger, my test statistics gets bigger, all things held equal, okay? What about as my sample variance? As my sample variance increases, what happens to my test statistic? It gets smaller, right? I'm seeing more variability in my sample, which then will drive up that standard error, which will drive down my test statistic, and then my sample size. As my sample size gets bigger and bigger, what happens to my t-test? Or my test statistic, all other things held equal. Yeah, right? Is this going to drive down my standard error? And as my standard error drives down, if this is all the same in terms of difference, that's going to make my test statistics start getting larger and larger and larger, right? So if I find a 5-point difference between my observed, my sample and some reference value, right? As that sample size gets bigger and bigger and bigger and bigger, it's likely to drive that t statistic up. So I can find the same magnitude of effect in this group versus this study versus that study. But if one study has a much larger much larger sample size, all things held equal, it's going to drive down that standard error and make that test statistic larger. Larger the test statistic, more likely it is that I'm going to be able to claim evidence for an effect. Okay. So again, all sort of looking at these ratios and these tests, as you start to sort of piece this apart, you're like, okay, yeah, I can start to see how this actually literally works in terms of changing values of my tests. All right. Quick word on degrees of freedom. Anybody got a handle on degrees of freedom? Yeah, degrees of freedom. We hear it all the time, right? It's kind of a weird thing. Like, what is this whole degrees of freedom nonsense business? Okay. Degrees of freedom from a statistics theory standpoint, we're talking about the number of values in the calculation of the statistic that are free to move around. Okay. So let's say the following, this is true. X plus Y plus Z is equal to 24. Okay. Elizabeth, what's X equal to? Sure, right? That's awesome for you. So what is X equal?
4.
4. X is equal to 4 plus, Amanda, what is Y? 10. All right. Plus Teresa. Okay. Well, now all of a sudden we ran out of room, right? Elizabeth lives in America. Amanda lives in America. Poor Teresa, by the end of the thing, she doesn't give America. She's got no freedom, right? you're no longer free to choose whatever you want to do and chart your own path, right? You're constrained by the decisions of these two. So what we've got is, by the time we get there, sort of infinite possibilities for X, Y, and Z first. Then still infinite possibilities. Second, by the time we get to the third, we're down, right? We've got nothing else to do, right? So we're locked in. This is essentially what our degrees of freedom entails, okay? So how many degrees of freedom, Emily, does this statement have? 2 degrees of freedom. By the time we get to that last one, it's already predetermined, it's set. There's no more flexibility with this, right? And so this is essentially what our degrees of freedom is talking about. So in the case of our single sample t-test, okay, this is a 1 degree of freedom test. To calculate our degrees of freedom, we take the sample size and we subtract 1. That gives us our degrees of freedom for this test. And so this is based on the calculation of our variance. So if we go through the single sample t, we're only calculating a variance estimate here, right? And we know that our variance is a function of deviation of each score from the mean. When we're going through and calculating variance, remember, first thing is calculate all those medians scores, right? And then we go through and square them, sum the squares, divide by, so whatever, we go through the variance, right? But because the sum of those deviation scores has to be 0, right? Mathematically, it must be 0. I'm free to choose all of my X values in that calculation until I get to that final value. And whatever that final value is, it has to make the sum equal to 0. And so that's where we lose that degree of freedom. That last value is fixed. It's not free to vary. And because we're only calculating one variance for our t-test for our single sample t, then we've got the number of people in our sample minus 1 degrees of freedom. Just to try and demystify, degrees of freedom are all over the place. Just trying to demystify kind of what that is and sort of conceptually what's going on with this. Okay. All right. So we've got an example here. Let's say that we've got a local library. We're doing a lot of library stuff. We're back at the library here. Local librarian claims that on average, books in a library are 20 years old. Okay. And to test this claim, we've got a methods class going on. We've got a student randomly selects 20 books, records the publication date for each. And what we see is we have a sample with an average age of 23.8 and a sample variance of 67.5. Okay. And so what we want to do with this is we want to state in a sentence the null hypothesis being tested. We want to state the null and alternative hypotheses in symbols. Calculate a 95% confidence interval for the estimate of the book age in the sample. We're going to conduct our hypothesis test at alpha equal 0.05. And then we're going to summarize our conclusions with respect to the larger research question. Okay. Remember that we're never just doing statistics for our health. Like I like quant stuff, but I rarely am I just like cranking out t-tests by hand just for the heck of it, right? We're doing this to answer some question, make some inference about something in the world, right? And so always making sure that we're not just saying, oh, there's a difference or there's an effect or anything along those lines, wanting to make some conclusion about sort of what it is that we're looking at here. Okay. So we'll get to this sort of what is, I guess, Matt, what is for this problem, what is our null hypothesis?
The local library are not 20 years old.
Yeah, or my null hypothesis.
Well, they are 20 years old.
Right.
Zero.
Right. So, and again, when you're going through and talking about this, what I sort of want to make sure that you're sort of letting me know that you know that what we're talking about is population values. So what I would probably say something along the lines of null hypothesis here is that the population of books contained within the local library has an average age of 20 years. And that lets me know that, so we're not talking about samples, we're saying that the population, all of them, has an average age of 20 years, right? And then if we wanted to do this very quickly in statistical notation, we would say null. We say mean books equals 20. Alternative hypotheses, books or age or something like that is not equal to 20. Pretty easy, straightforward. Okay. This, I can go through and crank those out without thinking about things or not knowing anything about anything. What I want you to give me a statement of the null hypothesis is what you're sort of letting me know that you understand what we're actually testing or what we're trying to infer from this, and that you understand that what we're talking about is population values and not so whatever's going on in my sample, right? Because if I'm just talking about my sample, Teresa, is that number 20? No, okay, I don't have, I can just look at it back together. Sample means not 20 because the sample means 28.3. Simplifies things a great deal, right? But that's not what we're doing. We're trying to infer something about the population and the population of books and their mean age. And so we're going to go through and do some stuff here. Okay. So in terms of calculations, just to kind of speed things up, how I set this up, right? So here, got our sample size, got our mean, got my variance, right? First thing I got to do, if I'm going through and I'm calculating my, want to calculate a confidence interval or a statistical test, what's the first thing I need to calculate? Someone shout it out. Standard error. Yes, that's fun. Yes, we do need the standard error, right? Right here, right? So first thing we're going to do, calculate our standard error, take the variance divided by the sample size. That's going to give us our standard error. Emily, what's the standard error? How do I interpret that standard error? That is true. What does that mean?
That given our a value of the sample taken has the plausibility of being between the values of 28.8 plus or minus.
Okay, we're starting to get into some confidence. Basha, in for the save. How do I, what's the interpretation of my standard error?
Isn't that the standard deviation?
Yeah. So if I were to grab any two average samples or any two random samples of size 20 from the library, how far would I expect on average those two sample means to deviate from one another? Yeah, this many. So I would expect about just a little under 2 years. So it's telling me of all possible samples of size 20 that I could pull from the library, if I were to do that, and then I were to plot out all the means, my standard error is just the standard deviation of that sample distribution. And that on average, I would expect any randomly selected sample of size 20 from this library to be about 1.8 years away from the true population value. So again, what I like about this is giving like we all understand how old something is, right? So putting sort of some of these statistical sort of figures into something that actually has real meaning as opposed to sort of the random score on the X, Y, Z, Q. Okay, so we'll go through, calculate our standard error. We then go through and we grab our confidence bound. So we've got our mean value plus or minus 2.093 times my standard error. Okay. Sam, where did I get 2.093? Yeah, exactly. If I go through and I pull up my T table, right? And so I've got an N equal 20. How many degrees of freedom in this test? 19, right? And so if I go through, look at 19 degrees of freedom, P equals 0.05, I get 2.093. That's my critical value. Yeah.
Is it 19 because you're subtracting?
Yep. So I got my degrees of freedom for my single sample test. Number of participants -1. That gives me 2.093. That's my critical value. This is where if we're running like Z stuff at 1.96, right? But here, because I've been working with small size, we've only got sample size 1, right? And so 2.093 is noticeably larger than 1.96, meaning that my test statistic has to clear a larger threshold in order for me to say, oh, I have something, or I favor or I reject the null relative to my Z test. And this is really at the heart and soul of sort of the problem that Gossett was trying to address. If I just use normal curve Z stuff with small sample research, it ends up not working out the way it should, right? So went through, plug this in and run this out, and I get my confidence bound here, okay? Amanda, can you give me an interpretation of our confidence bound here?
Well, it's plausible that the average book age is.
Yeah, okay, good. And again, so as we're starting to work through with some of these, like I don't want you to like sometimes I sort of had an unintended side effect of people like shotgunning the word population and everything, like it just pops up in random places where it doesn't fit. But generally, when we're talking about our confidence boundary, I wanted to say basically mean age based on this data, mean age of population of books contained within this local library. We're getting estimates of a lower bound of 19.96, upper bound of 27.64, something like that, right? Just letting me know that we're, because I don't have to create a confidence bound around the sample. The sample is the sample, like that's the number, right? We're saying that based on these data, our data would support estimates of the population value anywhere from a low of about 20 up to a high of 27.6 or something. So we've got this, and again, what was my reference value under the mean? Anybody remember? What was the value for my null here? What was it? 20. Okay. So based on this confidence bound, Emily, do I need to even run through my t-test to tell me if I have something that's statistically significant? No, why not?
The lower confidence bound is just under 20.
Yeah.
Your confidence bound is almost 80.
And so is my p-value going to be less than 0.05? Is 20 a reason, based on my confidence bound, is 20 a plausible estimate?
It's possible.
Okay, and so that's the null value. So in this situation, would I traditionally reject or fail to reject? Fail to reject, right? Because if the local librarian says 20 years, 20 years falls in there, right? So this is the thing. Once I got my confidence bound, like I don't even, the only thing that I'm going to get out of my test statistic is a point estimate of my p-value, right? But if I'm just sort of trying to sort of determine, make it sort of which decision I'm going, like I don't even, this is just kind of gravy here at this point, right? Okay, but I've asked you to do it, so we're going to go through and do it. So here you're going to calculate my t-statistic, easy peasy. I've got everything that I need, right? Here's my mean. There's my reference value under the null. That's my standard error. Calculated that out. I get a value of 2.096. My critical value, 2.093. This falls just beyond that. And then if I go through and I want to calculate an exact p-value from this, there's a p-value calculator. This graphpad.com is sort of one that I use, but there's 1,000 of them out there. It doesn't really make any difference which one you use. If I go through and I put in my test statistic, 2.069, and my degrees of freedom, I'm going to save someone some confusion and headache. Make sure that you're using your test statistic here, not your critical value, because if you plug your critical value in there, you'll always get 0.05. So just make sure you're clear on that. But we go through and do that. If I compute my p-value at p equals 0.052. Questions on any of our calculations here? So again, same thing as we've sort of been doing before. So in the previous examples, we're just going through and running our test statistic. Okay. So what we now need to do is sort of from what I asked you to do, kind of put this all into a brief summary. So our null hypotheses, mean age of the population of books contained in the local library is 20 years, right? Here's my statistical notation, my confidence bound, my critical value, my test statistic, my p-value, right? And so now what we want to do is we want to pull all this together in something that's kind of meaningful and start to address the question at hand, right? And so this is my attempt to kind of take these various pieces of information and put it into something that actually communicates information, right? So we say the average age of books sampled for this study was 23.8 years, with population estimates ranging from 20 to 27, identified as compatible with the data. Here I've just kind of dropped in. Notice that at no point in any of this stuff have I started talking about percentage likelihood or anything along those lines or confidence level or anything like that. I just dropped, like, if you want to know sort of the confidence level, you just look at that. It sort of prevents confusion, right? It's important to note the precision of these estimates, sort of margin of error, that's my plus or minus, right? Interval of range is 7.7 years, is limited by the small number of books in the sample. While the upper limit of the interval sports estimates that exceed the library's guess by more than 7.5 years, estimates near 20 years remain plausible given the current data. Its consequence results are generally inconclusive regarding the extent to which books in the library are close to the expected age of 20 years. And then here at the end, we just kind of tack on stuff. Okay. Anybody confused about sort of what's going on? Does anybody have like questions about, did I miss anything or not communicate anything in that summary?
Critical value again, I understand the.
The critical value?
Yeah.
Oh, that's just from my,
That's the table.
that's from
Okay, that's
yeah.
the table. Got it.
But so in reading this, was there anything that we forgot or didn't sort of include, or is anything that's confusing about that? Okay, so we managed to go through and sort of describe results of this test in quite a bit of detail. It incorporates a lot of stuff without ever using terms statistical significance or saying that something is or isn't anything, right? If we go through and read this, we're saying, well, it's kind of inconclusive, right? If someone is hard up and really wants to know a p-value, it's right there. They can look at it. But I'm pretty sure people don't need to know. Everybody clear on numbers that are below 0.05? Above 0.05? Cool. And we don't have to label them as significant or insignificant because it doesn't matter because I'm counting on the fact that people can just look at it and sort of determine whether or not it's something that they want to interpret as an effect or not, right? So what we're just trying to do is kind of pull this all together and sort of use the information at hand and say something meaningful about a semi-trivial question on sort of how old these folks are. Questions? All right, cool. So complementary statistics, okay? These are things that we're going to start to build into our calculations, interpretations, try and improve sort of the types of things we can say about the question. So first thing is going to be our effect size, okay? Most of you are probably already kind of familiar with effect size, what this is doing, what's happening here. Effect size is essentially just an estimate of the magnitude of the effect in the population. So independent of sample size. Our test statistics are 100% dependent on sample size. If I want my sample statistic or my test statistic to go up, what do? I just collect 1 billion people and that statistic is going to go through the roof, right? My effect size is an estimate. Now the precision of that estimate is going to change. It's going to get more and more precise as my sample gets larger and larger and larger, but it's not calculated as a function of sample size, okay? Like any other statistic, my effect size is an estimate of a population value. Somewhere out in the universe, there's an effect size for the difference in height between men and women in the US who are adults, right? There is a real actual effect size for that. We will never know what that is. What we're doing with our sample is calculating an estimate that tries to represent what that effect size is out there in the population, right? Now, we can start to sort of move back and forth in terms of between different metrics, but the tricky thing is, and sort of my sort of working hypothesis, why effect sizes haven't caught on sort of as easily as like p-values and things like that, is because it's hard. If I'm working with, even within means-based analyses, there's like 3 or 4 different metrics that I could use. If I switch over to ANOVA, now I've got a different effect size. If I'm working with chi-square, it's a different. If I've got a correlation or regression, it's a different. So it's hard to compare across groups. Now, when we're going through and we're running our meta-analyses, there are conversions that we can go through and sort of do, but know that as I'm working through different types of analyses, we're going to be working with different effect size metrics, okay? But what this does is it starts to help us augment our interpretation of our inferential statistics, okay? So our effect size for our single sample T, a couple different options. One, we can just look at the raw difference between the mean and our population value as our a simple measure of effect size, right? So let's say if I'm working with units that are relevant, right? And if I say, here is the average income in the US in dollars, and then I say, here are my sort of random sample of 1,000 women from the US, and I look at their income or their salary, and I compare that to the average for the country, that's going to give you a dollar amount that's going to mean something that's very sort of has intuitive value to it, right? I can go through and look at that, and if I see that difference between women's average salary and the national mean is, say, $100 a year less. Are we identifying that as something that's sort of meaningful and important? Probably not, right? In the sort of over a sort of yearly salary, $100 probably isn't a ton different. But if we find probably more accurate that women make, say, $7,000, $8,000, $15,000 a year less than the national average. It's kind of tricky because women are included in the natural average, but then that starts to become sort of something that's much more meaningful, right? In psychology, we're often not working with metrics that have intrinsic sort of meaningful, some sort of meaningful value, but sometimes we are, right? We're talking about alcohol consumed, or if we're talking about sort of weight, mass in pounds or something, there are situations where we can start looking at things that just the raw difference there starts to sort of provide a meaningful metric of effect, right? Which is cool, and so we should have those and be reporting those if we are using meaningful metrics. However, for a lot of the stuff that we're doing in psychology, a lot of it's sort of arbitrary measures, right? And it's hard to get a good sense of whether or not this is something big or different or small or something along those lines. And so what we have is our standardized metrics. Cohen's D, what we're doing is we're now taking a look at units in terms of standard deviation differences, right? And if we think about that normal curve, that standard deviation difference starts to have some intrinsic meaning to us as statisticians, right? Amanda, if I say something is 3/10 of a standard deviation different than something else, is that very big? Not too big. If I say something's 4 standard deviations bigger than something else, that's massive, right? So what we're doing with Cohen's d is we're going through and we're taking that difference and we're putting it in a metric of standard deviation units, okay? And so now all of a sudden this starts to have sort of more meaning if you kind of understand that normal curve and what a standard deviation unit is, okay? So what we've got here is our formula for calculating d. Really easy. Take our mean minus our reference value, and we're dividing by a standard deviation estimate. Easy peasy, right? And I'm going to interpret that as standard deviation unit difference, right? So books in the library were 0.8 of a standard deviation above the expected value under the null hypotheses, right? That's 0.8 of a standard deviation, 0.8. That's decent sized, right? What we've got are benchmarks provided by Cohen, who said never, ever, 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 ever use these as hard and fast rules. So immediately what we did is we use these as hard and fast rules without ever thinking about sort of the metrics or what that means. I have you read a paper that's really cool when small effect sizes are impressive. There's a really cool paper, right? And sort of talking about just because it doesn't have to be a massive effect size in order to be kind of interesting or cool. But what we can do is start thinking about the practical impact of some of our effects. That, and this is a metric that's not given by our statistical tests, right? Interpretive standpoint, standards or benchmarks for D.2. This is a small effect. Cohen, in his book, talks about this and I think he's just trying to relate things that kind of people understand. So talk about this is consistent between the height difference in height between 15 and 16-year-old girls, right? If I took a bunch of 15-year-old women, 16-year-old women, sort of put them together, there's going to be systematic differences there just based on development, but I'm probably not going to, it's not going to be something that's going to be clear and obvious, right? Medium effect size is about 0.5, half a standard deviation. Here we're starting to get something that's visible, sort of noticeable, sort of by the eye, difference between 14 and 18-year-old girls. Large difference, D equal 0.8. So this is something that's going to be very clearly obvious, right? There's a clear discrepancy between sort of these two groups or sort of this and a reference group here. So these are general benchmarks for interpreting sort of large, medium, small, medium, and large effects. And these are useful and help in terms of referencing things, but always remembering that sort of the importance of an effect sort of depends on sort of methodology, the research area, the question, and things along those lines. Okay. Also, if I wanted to, someone had asked previously, I think maybe Emily, about like, oh, well, so if I'm just reading something, is there any way, what do I do if people don't, if I want to know an effect size and someone doesn't report it and things like that? If someone gives you a t-value, we can get an approximation of D just by knowing the test statistic and the sample size, right? If I take a t-value divided by the square root of the sample size, that's going to give me an approximation of D, okay? Now, you notice I asterisk this. This asterisk means that for your own stuff, it's actually calculated out. Like you have the information, just calculate it out, right? Don't take your, this is an approximation. They'll add up pretty closely. But if I'm going through and I need to say I'm trying to run a power analysis for my thesis, and I want to know, am I going to have adequate power to go through sort of how many people do I need? What's the effect size I'm chasing? But Josiah et al. 1963 didn't actually report an effect size because we didn't do that at the time, right? If they got a test statistic, I can go through and actually calculate an approximation of that effect of what it should be. Okay. Questions about effect size? All right. Oh, Wilkinson sounds like Mr. T to me, right? Always provide some effect size estimate or reporting p-value for primary outcomes. Stress again the reporting and interpreting effect size in the context of previous reported effects essential to good research. Okay, this is starting to become, and again for experimental folks, right? So CJ for like stuff that you and Sean are doing and stuff like that for the journals? Are they generally wanting estimates of effect size when you're sort of submitting and things like that? Yeah. It's starting to become more and this is what like journals are going to police it. If journals make you do it, then you're going to do it. If they don't, you might not. Clinical is still behind. Like we often get away without sort of reporting that stuff, but experimental journals will, and some clinical journals will as well, right? Or people will ask you for these type of things. So good to be familiar with it and just start doing it as just kind of routine habit or thinking about magnitude of effects. All right. Other thing we'll probably finish up here, talking about S values, okay? So we talked about arguments for interpreting P as a measure of statistical compatibility of the test hypothesis and the observed data given assumptions of the model. A is sort of all the other auxiliary stuff that we're talking about, right? But what we can do mathematically is we can take that P value and say, this is literally a gauge of the extent to which these data are discrepant or consistent with my null model. If my P value is very, very small, it says that these data that I've obtained are extremely incompatible with my model. If I got a P value that's very, very large, I'm like, yeah, these data are relatively compatible with my null model, right? Kind of a nice, easy, and sort of efficient way to go through and think about P values, right? Problem is that the scaling of P is tricky. There's not sort of the increase in magnitude in evidence against is not equal across all units. Okay, so if I'm looking at the difference between P equals 0.01 and 0.10, that's a lot different than the difference between 0.90 and 0.99. Okay, so thinking about for people who, or if you know about like intelligence testing, like IQ tests and things like that, right? The difference between a score of 100 and 105, like that 5-point difference, means a lot different than if I was going to say 135 to 140. That jump from 135 to 140 is a huge increase, whereas the 100 to 105 is fairly trivial, right? Same type of thing for P, okay? And so the idea here is that problem is what we do is we use this bright line interpretation of P less than 0.05 as evidence for something that's very, very real, or at best something that we sort of don't know, right? And so what we often do is when we talk about statistical significance, we often assume this means something about the replicability and meaningfulness of an effect. What we can do is we can take these p-values, and this is outlined in the Greenland article, and turn that p-value into a metric that has more intrinsic meaning, something that starts to be more intuitive in terms of thinking about evidence against the null. Basically what we're doing here is we're taking, if we take, create this Shannon information value, it's a non-linear transform of P. If we take the negative log base 2 of P, and this is hard to kind of sort of go through, but it sort of mathematically converts over to the natural log of P over the natural log of 2 will give us, because log base 2 is hard to calculate in your hand calculators, things like that. This right here will give us a value that we can then round into a whole integer. And this starts to provide us with something that's a little bit more intuitive in terms of thinking about evidence for and against, okay? So what this does is this S value, we can interpret this as roughly the same evidence against the null hypotheses as observing S successive heads in a tosses of a hypothesized fair coin, okay? So going back to my trying to convince Teresa that I have a fair coin, and I'm going through and I'm flipping, right? And how many heads go through before you start to worry about maybe this is off base, before you're like pretty sure, and at the point where you're like, there's no way what I just watched you flip 150 heads in a row is not something that's possible if that's a fair coin, okay? And so what we do if we go through and calculate, I'm excited about this again. I like being surprised by myself. I'm like, oh, I forgot that was coming up. If we're saying sort of like a t-test with 50 degrees of freedom, here's our different t statistics, here's our p-values, here's negative base 2 log of p that we calculated, and then we just round that to the nearest whole value, and this is my S value, right? So if we go through and we look at for us a t-test with 50 degrees of freedom, right? You say this is, we're not to between sample t-test yet, but I've got a comparison of two groups. Let's say I got 26 people in one group, 26 people in the other, and I run a comparison of the two, and I find that I get p equal 0.05. Okay, this is our threshold for interpretation, right? This is where we can say that we've found an effect, right? But if I take 0.05 and I calculate transform that into an S value, I get a value of 4. Okay. So Sam, if I had to say I got this fair coin, right? And I flip a heads and it's heads. Well, I flip a coin, it's heads. And another head, and another heads, and a fourth heads. How confident are you that sort of my coin is not fair? Yeah. Yeah, probably starting to get a little bit suspicious, right? Yeah. Are you willing to bet the house that this coin that I have is not fair? No, right? Would you be willing to spend, say the next 4 years of your life dedicated, invested to research on sort of this coin is not being fair? No, probably not, right? Now, as we go through and we start taking a look, so then as this starts to go, we've got 0.01. Usually we get 0.01. We're pretty excited about 0.01. This is 7 consecutive heads, 0.005, 8, So we start to, by the time we get like here, like if I got 17 heads in a row, I'm like, no, that's not sort of happening, right? But what we can do is use this as a way to start thinking more carefully about the types of effects that we're seeing and sort of evidence against sort of the null hypotheses that there's nothing going on, that there's no difference, that there's no association, so on and so forth. Okay, helps put things into a little bit more perspective in thinking about how confident am I in the evidence against my null hypothesis here. Okay. Questions about these S values? Other thing we'll do is we'll finish up here with Bayes factor. Thinking about sort of that inverse between what we are trying to ask and what our tests are telling us, right? What we want is we want to use this p-value to ask our strength of evidence question. How strongly does the evidence from the data favor our alternate hypotheses versus our null hypothesis, okay? But our test statistics don't do that. They only provide a test of the null, right? Assuming the null hypothesis is true, assuming there is no difference, or assuming there is no association, what's the probability of observing these data or something more extreme, right? But that's not the question we want to ask. When we start to get into Bayesian statistics, that's where we start directly answering this strength of evidence question with our Bayes factor. Now, we're not going to get into Bayesian statistics because I can't, because I don't understand it, because I've never sort of tried to go through and do things. But what we're trying to do, what we're wanting to do here is look at the average likelihood of the data under the alternative hypotheses versus the average likelihood of the data under the null, right? And this is going to give us an odds ratio, okay? Calculation of our Bayes factor. The thing that makes Bayesian stuff hard is what we need to have is a prior probability of the data under the alternative hypothesis. And this is just something that's very difficult to do, right? We often aren't working with enough information to estimate an effect size, much less the probability of the alternative hypotheses. We also have an infinite number of alternate hypotheses against a point estimate. It starts to complicate things, right? But Benjamin and Berger proposed a method for calculating an upper limit of our Bayes factor, like under the best circumstances, assuming, and this is off best of circumstances often involves equal probability of the alternate versus the null, right? Think back to that base rates question, not 98% versus 2%, right? 50-50, best case scenario, what's the upper limit of this Bayes factor? And what we can do is we can take yet another nonlinear transform of P and start to convert this into what Benjamin and Berger are calling Bayes factor bound. And Bayes factor bound is going to represent the largest possible Bayes factor consistent with the observed p-value, okay? And we would interpret this as the odds of the strongest case for the alternate relative to the null based on the available data, okay? And so this is still tricky. This is still like best case scenario. Are we ever confronted with the best case scenario? No, we're always confronted with the worst case scenario, right? It's always constantly breaking down. But if we wanted to give an upper limit on that Bayes factor, what we can do is we can take 1 over negative base E. You know what base E is? Mathematical constant. It's like pi. It's just a number. It's 2.1817, something like that, right? It's on your calculator. So you can take negative base E times your p-value times the natural log of p. This will give you your Bayes factor bound. Okay? And what we can do is we can interpret this as the strongest, representing odds of the strongest case for your alternative relative to your null. And now what we've got is something that actually answers this. How much, based on the data we've collected, how likely is the alternative relative to the null? And so here's some examples of what we've got here. So we've got, again, for right at p equals 0.05, our S value is 4. We've got a Bayes factor bound of 2.46. Okay. Anybody do any stuff with odds ratios in their research or sort of work with that in their areas? Okay. Odds ratio is pretty handy, actually pretty slick. We ought to use them more, right? But basically, what we're saying is there's so for, let's say, 0.005 here, our Bayes factor is 13.89. So we would say that the likelihood of our alternative hypothesis is at most about 14 times that of the null. That's pretty good, right? So the odds of this versus that is 14 times this versus that. If we go down to our 0.05, we would say the likelihood of the alternate hypothesis is about 2.5 times that of the null hypothesis. That starts to put things in perspective. I mean, it's better than not, right? But it's much less than as soon as we start to work down here, right? For our P.005, we take this number, right, and subtract 1 from that and say the alternate hypothesis is 1,289% more likely than the null. Okay. So if we have even odds, what does that mean? If A is equally likely as B, what's our odds ratio there? 1, right? So we always take our odds ratio and subtract 1 if we want to calculate that over the percentages. So if we've got an odds ratio of 2, I would say the likelihood of A is 100% more times more likely than the odds of B, right? So we're just taking this, moving the decimal, subtracting 1, moving the decimal, and saying 128, 1,289% more likely than that. So this much more sort of evidence against the null hypotheses than, let's say, p equals less than 0.05, right? But the problem is when we're actually doing research, when we're publishing things, right? Katie has p equals 0.049 and Elizabeth has p equal 0.002, right? Tend to treat those as equal evidence under the null because it's all less than 0.05. And so we run into big problems in terms of interpretations and understanding what that means, right? Have you read a Greenwald paper that talks about sort of the relation between p-values and replicability. And again, that's under a perfect case scenario, right? And you can't say, oh, this is one thing is that's another. But if I'm looking at that, we can start to sort of use that p-value and sort of infer strength of evidence against the null hypotheses and our different stuff, okay? All right, cool. We'll stop there. We'll pick up with Bayes factor, and then talk about some more posterior probability stuff. Then we'll get into our actual t-test. So what we'll do next time is start with actual SPSS stuff. We'll start working through actual analyses and things along those lines. I've downloaded or uploaded all the handouts and all the sort of printouts and things like that. If you're cool with electronic copies, awesome. But if you would actually like handwritten notes to go through and write on, let me know and I'll go through, print those off so that you don't have to, and we'll be good to go. Okay, awesome. You all are champions. Thank you so much.